Hello all and good day. And my name is Karthikeya Jayadurga Prasad Raju, and I am presenting my presentation for the project that I have done for CP 5170 real-time systems for spring 2020 semester. So this project is titled Real-Time Analysis and Design of Scheduling Algorithms for Power Electronic Systems. So coming to the motivation of this project, we aim at controlling two DC-DC converters running at two different voltage specifications of 3.3 and 2.5 volts from a common input of 8 to 15 at a power rating of 10 watts. So that's the most important thing that we are trying to do in this project. So the aim of the project is to control these two DC-DC converters running at two different frequencies by a single embedded controller. And so we are trying to assess the load that the embedded controller takes when it is controlling two different converters running at two different frequencies. So coming to the accomplishments we have achieved, well, we have successfully been able to run both the converters in closed loop while maintaining constant data communication link with a Linux terminal. We were able to control the converter while data streaming. We were also able to print the health data being buffered to the terminal, and this health data would mostly comprise of the status bits within the for the converter, and this status bit is custom designed for the converter. And also we are trying to print out the temperature of the MOSFETs and also the voltages that the converters are controlling. Now we were also able to successfully isolate the converter from faults, and also the fault would be prompted immediately on the terminal so that the user can discern what kind of a fault it is and act accordingly. So coming to the implementation details of the converter, two buck converters were designed with two different frequency and voltage specifications for each converter, and a PCB is designed. So this is the PCB that we have. We are trying to put them in closed loop so that even if we change the input voltage from 8 to 15, these emit a constant output voltage of 3.3 and 2.5 respectively, and fight against those input voltage variations. So this needs a lot of control engineering too, and we have also done that actually. So coming to the project goals, we are trying to control two DC-DC converters in voltage mode control. This is one of the types of control schemes used in power electronics for DC-DC converters, and each DC-DC controller has its dedicated control law dictated by a digital controller implemented in direct form realization of a tuned controller transfer function. This transfer function is designed in MATLAB and is out of the scope of this course, but has been designed previously, and without which this project wouldn't have been possible. Now coming to the failure mode detection, we have a MOSFET over temperature. So whenever there is a very high temperature on the MOSFETs, we need to isolate the converter from operation. And also if there is an output short circuit, so if this output that these converters are generating, if they get shorted out, we need to also be able to isolate the converter. We need to also be able to communicate with the Linux terminal to display messages and enable online variation in parameters. So that's also something that we need to do. So coming to the real-time performance specifications, we have run the system and we have found that the ADC and the ADC1 and ADC2, which are basically the control loops of the two converters, consume the maximum utilization of the processing power, which is 37.2 and 37.2% each, and each have a same period and same execution time. We will talk about why we have same period and same execution times for both of them shortly, but that's the gist right there. Timer 2, which is basically something that takes care of temperature scanning and other housekeeping functions like toggling LEDs and also trying to check whether the gate driver is healthy or not. All those functions are being done by timer 2 as an interrupt, and it keeps on scanning at that interrupt rate. Then we have the UART transmit and receive, which are responsible for the user terminal communication, and they actually do not consume a lot, 0.018% and 0.07%, and because this timer is actually also running at a very low frequency, and even the execution time is very low, its utilization is actually negligible. And finally, coming to the external trigger, it's actually a sporadic event. It doesn't occur periodically, so the utilization cannot be defined for this, to be very frank. The total utilization is around 74.88%, meaning that we have room for more tasks to be added, and also maybe this could be scheduled using an EDF or an RM, which is also known as a rate monotonic scheduling algorithm. However, the prioritization order for these interrupts was selected in such a way that UART receive and UART transmit had the highest priority, because communication to the user was given the highest priority, and so this means that we have an arbitrary priority order that we are trying to give it. And also similarly, we have ADC1, ADC2, and ADC3, which are responsible where ADC1 and ADC2 are responsible for the voltage acquisition and control loop actuation, and ADC3, which is responsible for temperature acquisition, are given the next priority so that the UART terminal responds at the fastest rate. I will talk about the external trigger shortly, but then we have the timer 2, which is responsible for triggering ADC3, and that is right here. And it has the least priority, and it also does all the housekeeping jobs in the controller and the converter system. The external trigger is given the highest priority in the whole system. However, it cannot be classified as a cyclic job, so it is given the highest priority. But actually speaking, whenever the converter is working in a healthy condition, the first priority, the second priority, and the third priority are given to the UART receive, transmit, and ADC interrupts respectively. And also, to be more frank, UART receive and transmit are given the same priority because they come under the same type of interrupt, previously succeeded by a receive event. So we have the receiving event happening first, and then the transmit event. So for the prioritization, we have done it that way. But and coming to the justification, why are we trying to do that? Well, high ADC interrupt preemption priority will cause significant delays in the UART response times and can lead to UART receive failures upon timeout by the PC. So that's actually the main reason why we are pushing the UART interrupts to a higher priority order than the other ones. So coming to the demand functions for these, well, we are actually having an arbitrary scheduling algorithm, and so we need, and so we cannot use, we may not have a particular schedulability analysis for it. So, but we know that the demand function, or basically the time demand analysis approach, is a very arbitrary approach, and it can be used for any kind of scheduling algorithm. And so these are the weights that we these are the demand functions that we come up with for them, and they have been written here, and they follow the similar priority order that we have given. Also, it is important to note that there were some phases previously, and those phases are not here anymore because we are actually considering the critical instance. So if we can actually remove make the phases 0, we can then consider the critical instance, and these demand functions correspond to the critical instance. And if we can ensure that we can meet the deadlines of this critical instance, then we can meet the deadlines of any other instance. And so by that logic, these demand functions are justified. And we will show the demonstration of the firmware now. Okay, so coming to the demonstration of the system, we have opened up two instances of the Linux terminal. And these two terminals are actually the same program, but have been opened up in two different terminals so that we can use the data stream feature here. So once I start the data stream feature on this, the microcontroller starts buffering the health data through the line back onto the PC. Whereas here, this is the stationary terminal with which we can control the commands by sending single commands to the microcontroller. Coming to the health data, so this is the supply for the gate driver, and this is the main supply for the converter. And the voltage is actually finally being dumped into these resistors. So those are the load resistors right here, and this is the converter right here that I have demonstrated before. And this is the oscilloscope that's sensing the signals. Now, so this is the data streaming that's happening, and we can already see that the raw ADC temperature reads are actually being shown here. These are 12-bit values, and so the temperatures are nominal and nothing is working right now. And similarly, we can see that this is the parse data for converter 1. The converter 1 is inactive. All of these are inactive. These are all the status bits. So this is the status bit for converter 1. These are the status bits for converter 2, and these are the online parameters that we are reading. And the voltages are 0, so they are not working right now. So we can switch them on. So the first thing I would have to do is also go ahead and activate the controller sections for both the converters, and then start both the controllers, and we would see that it wouldn't switch on because the gate driver is in under voltage lockout, as it can be seen right here. So we can see that the gate driver 1 is inactive, gate driver 2 is also inactive. But if I bring the voltage up, so I'm increasing the voltage and I'm going to look at it, and once I cross around 5 volts, the gate driver sections become active. There you go. And now we can start controlling our signal, controlling our converter plant. So that's one thing. So the next thing is to see what data we are getting. So I also have to start converter, both the converters, and so the converter 2 is also now active, and it is trying to regulate the voltage at 3 volts, which is approximately where it is, and the second converter is regulating the voltage at 2.5 volts. And now and that's exactly what we are looking at even on the oscilloscope. So this is the converter 1, this is converter 2, this is at 350 kilohertz, this is at 500 kilohertz, this is the signal at 3.19 volts, and the other one is at 2.6 or 2.5 volts approximately. And now if we start giving input voltage disturbances, you can see that the duties of the converters change, and we are actually fighting against the input voltage variations. So basically we are trying to maintain the output voltage at a constant level. And we can see that converter 1 is kind of not optimally tuned, so it kind of shows the shows those oscillations and then settles down, whereas converter 2 is kind of rock solid, and it maintains the output voltage at 2.5, and even if it has a better response, So let me go ahead and switch these converters off. So the converters are switched off, and everything goes back to inactive, and everything is inactive now. So that's basically how everything is working here. Now if I switch them on again, everything gets on updated online, and now the same data also is shown here. So if I switch the 2.5 volt section on, and if I'm actually varying the voltage, as you can see, I'm trying to change the voltage, and we can see that we're also going to get the same type of data right here. So it basically means that the controller is controlling properly. Because it's an external trigger, if I press the user button right here, we go into the overcurrent event, and once we hit the overcurrent event on both the converters, the converter status is turned back to inactive, and everything is turned off. So basically that's working too. So and for example, if I reactivate both the converters, they work, but once again, now let me go ahead and press the switch. You will see that everything will become inactive. I have pressed it now, and there you go. You see that the overcurrent event has been flipped to true, and also the converter 1 status is now inactive. So, and everything is switched off. So basically that's how this is all working. It should also be noted that the converter is not completely loaded right now, the processor I mean. So we can actually load the whole processor, and this is the worst load that we can put on the processor, by activating all the sections in the code, and the processor is actually able to sense the temperatures, it's able to control the voltages, it's sending the voltages back, it's sending all this data back, and it's working perfectly without any problems, and everything is working at its own rate. And so the arbitrary scheduling algorithm is a success. Coming to the conclusions then, the arbitrary priority algorithm was found to be successfully working, as it has already been shown, and all the processes worked seamlessly on their own rates and at the specifications at which the real-time system was designed. However, there are definitely a few weaknesses to this system, and they are that the sampling at the target frequency was not possible. The ADC interrupts were all tied up to a single interrupt priority level, and therefore was not possible to sub-prioritize the interrupts. Which leads to the interrupts being tied up and occur at a single rate than at their respective rates, which is less than ideal, to be very frank. And also the floating point controller was implemented here, which is processor intensive, and also the controller was being implemented with a linear data buffer that needs more data shifts than something that we'll talk about in the next slide, a post, which is a better application, and intensive usage of the HAL library, which is provided by STM. Though it's good for real-time operating system interfacing in the long run, it can take up a lot of context switching overheads, and it's not the most ideal thing there is. So coming to the recommendations to improve the performance, choosing a microcontroller that is tailor-made for power electronic applications, and one that can have separate ADC interrupt priorities than having a tied up interrupt, can actually improve the performance in our system, and we can individually service each ADC interrupt whenever it comes in, rather than the interrupts getting tied up. The controller uses a linear data buffer and needs all data samples in the buffer to be shifted right by 1 unit in the end, which consumes a lot of processing time, and a better application would be to use a circular buffered controller. And coming to the continuation of the recommendations, the controller also has a floating point multiplications and can consume the processor resources significantly. So therefore, a fixed point implementation of the controller is better suited for a signal processing layer of the application. And however, fixed point processing is a little complicated and has to be carefully designed. Also, using usage of assembler level directives as opposed to C language based commands to improve the execution time of the high speed interrupts can also improve the performance, because assembler directives are way faster than C language based commands because of the cross compiler tool chains involved and non-optimality in the way the C language is translated into assembler directives. So thank you very much for your attention, and please direct your questions to the mentioned email if you have any questions. Thank you very much, and have a nice day.